Hi everyone, welcome back. Last time we discussed the contributions of the ancient astronomers leading the way up to Ptolemy, who put forth a very precise way of describing the motions of the so-called wandering stars, that is, the planets through the heavens. And here we're going to discuss the contributions of the Renaissance astronomers, in particular Copernicus, Tycho Brahe, Kepler, and Galileo, who were finally able to successfully dismantle this system. So here's a quick little medieval proof that Earth doesn't move by Scipio Chiaramonte. Animals which move have limbs and muscles. Earth does not have limbs and muscles, therefore it does not move. Looks like a little bit of putting the cart before the horse there, some obvious logical fallacies there. But in any case, in this historical timeline, the 5 astronomers on whom we're going to focus in the rest of this unit are all kind of back-to-back, with Kepler somewhat in the middle, and Newton is literally back-to-back with Galileo. In other words, it's said that the day that Galileo died was the day that Newton was born. So maybe some reincarnation? Who knows? But in any case, in the rest of, or at least in this video, we're mainly going to focus on Copernicus, Tycho Brahe, Kepler, and Galileo, and save Isaac Newton for the next discussion. Now, Copernicus did not invent heliocentric theory. As we discussed in the last video, Aristarchus of Samos had invented the idea, or at least was the first really strong proponent of the idea that Earth goes around the sun back during the time of the ancient Greeks. But Copernicus took Aristarchus's ideas a bit further. A lot of history textbooks, unfortunately, give credit to Copernicus for inventing this model, but Copernicus himself did not even claim to invent it. He actually made it very clear that he was taking his ideas from other people. In particular, he noted the 6th century astronomer Capella, who made some attempts to improve upon Aristarchus's ideas, and he also noted Aristarchus himself. So, yeah, Copernicus was not trying to take credit, but unfortunately, negligent historians later on tried to ascribe credit to Copernicus for something that had been done 2,000 years previously. But in any case, Copernicus had a lot of these ideas for a while, and it's said that he was hesitant to publish these for fear of the consternation that it might cause within the Catholic Church, but eventually he was persuaded to publish his ideas before he died. He was persuaded by a bishop in the church to publish, and in so doing said, as part of his work, we therefore assert that the center of Earth, carrying the moon's orbit, passes in a great orbit in an annual revolution around the sun, that near the sun is the center of the universe. Any apparent motion of the sun can be better explained by motion of Earth. So, as we already mentioned, Copernicus did not invent the idea of the planets going around the sun. However, he did improve Aristarchus's model. And essentially, Copernicus's model is kind of a hybrid of Aristarchus's model and Ptolemy's model. Copernicus moved the sun off-center, just as Ptolemy moved Earth off-center. Copernicus moved the sun off-center. He revived this idea of equants with the idea that as planets go around the sun, there is a line that connects a point that's on the opposite side of the center of the circle from the sun with the planet, and that line always goes around with constant angular velocity, with the result being that when a planet is closer to the sun, it is going faster, and when it's farther from the sun, it's going slower. So this was a very big contribution of Copernicus. Now, this was simply a model. This was not a theory. A theory would explain why it should go that way. Why do the equant points work like that? That would actually not be solved until the time of Isaac Newton and Newton's law of universal gravitation. But at least he gave a mathematical model showing how, at least in the model, it could work in terms of the equant points. And this was a big advance. Now, unfortunately, just doing this was not enough to make his model as accurate as Ptolemy's. In order for Copernicus to make his model as accurate as Ptolemy's, he had to add some things to it that we're soon going to see. But some advantages are that, at least conceptually, it's simpler. In other words, you don't have to worry about epicycles to explain the retrograde motion of the planets. And it also gives a natural explanation of the fact that our sun seems to move against the backdrop of stars. In other words, Earth is going around the sun once per year. That works really nicely. And in addition to this, this gave a way of using geometry to determine the relative spacing of planetary orbits. Guess what? People during the time of Copernicus knew that Jupiter is 5.2 astronomical units from the sun. They knew that. They knew that Saturn was about 9.9 astronomical units. That was just something that people knew. They could figure that out. Now, I'm not saying that they knew how big an astronomical unit was. They didn't know the number of meters in an astronomical unit. They simply said that, yeah, Jupiter orbits 5.2 Earth-Sun distances from the sun. And Copernicus' model also gives a natural explanation for why Mercury and Venus never go far from the sun. It's like, well, they're orbiting around the sun inside of Earth's orbit. So we're never going to see them go far from the sun. We will certainly never see them rise when the sun is setting. It's just not possible. They would have to be on the opposite side of Earth from the sun, but they don't orbit that way. Now, some disadvantages. Copernicus' system was not able to account for the lack of parallax motion of the stars. After all, remember, that's what originally turned away Aristotle from the idea, the fact that there was no observed parallax. It turned Hipparchus away from the idea, no observed parallax. So they simply had to assume that the stars were incredibly far away, which it turns out they are. Now, unfortunately, another problem is that Copernicus' system originally was not as accurate as Ptolemy's. In order for him to make it as accurate as Ptolemy's, he had to add epicycles to the planetary orbits around the sun. In other words, making the system at least as complicated, perhaps more complicated, than the Ptolemaic system, in order to get the same level of accuracy. For this reason, in spite of popular belief, the Copernican system was rejected, generally speaking, in the scientific community at the time. It was an interesting idea, but overall it was rejected because in order to make it as accurate as what had been working for over 1,300 years, Copernicus had to make it more complicated. So why go with something that's more complicated when this thing that's a little bit simpler has been working for 1,300 years? Next up, Tycho Brahe, or just Tycho. Tycho believed in a geocentric universe, but he did believe that planets other than Earth went around the sun. So, Tycho believed that Mercury, Venus, Mars, Jupiter, and Saturn orbit around the sun, but that the sun orbits around Earth. He made extremely precise observations of the planets, particularly Mars, with the best instruments of the day. He was the last and greatest of the pre-telescope observers. In fact, he is the greatest non-telescope astronomer in history. Nobody has surpassed him. For a very simple reason. Right after he died, the telescope was invented. So everybody started using that. So Tycho noticed that the predictions of both Ptolemy and Copernicus, even in their most precise predictions, they were not sufficient to accurately reproduce the motions of the planets, in particular Mars, for reasons that we will discuss soon. So for more than 20 years, he measured these positions and got them to a very high degree of accuracy, to within only a few arc minutes. So remember, the moon's diameter is about 30 arc minutes, and he was able to measure the positions of these objects, particularly the planets, to within just a few arc minutes. He also made himself famous by making careful observations of a new star in Cassiopeia. He called it a nova, which just means new star. Although we now recognize that we later used this term for a certain type of astronomical event, and we now recognize that what Tycho saw was not that astronomical event. He actually saw something called a supernova, which was a star exploding. But when he saw this thing, he noticed that he was not able to measure its parallax. And, I mean, he could measure the parallax to figure out the distance to the moon, but he was not able to measure the parallax of this nova, this new star. So he concluded that this must be farther away than the moon. In other words, it's no meteorological phenomena or anything like that. He also did the same thing with comets. He realized that comets are not meteorological phenomena. In other words, they are heavenly phenomena, and that's because he could not he was not able to discern any parallax to the comets. In other words, no matter whether you were looking at them at sunrise or sunset, their position relative to the background stars remained pretty much unchanged, other than their general trending motion due to their motion around the sun, as we now recognize it. But in any case, his observation of this supernova, where the star destroyed itself completely, made him famous enough that King Frederick II of Denmark offered Tycho an island where he was able to construct an observatory. Now, if you want to see the remnant of Tycho's star, as it's now called, it's in this area of Cassiopeia, kind of near another star that actually is truly a star. And you would need a telescope, preferably a radio telescope or an X-ray telescope, and you would be able to observe this remnant. This is actually an X-ray observation that is pasted onto a backdrop of stars in visible light. But still, it's kind of cool, the remnant of Tycho's star. So, depiction of his observatory. And as I mentioned, he also figured out that comets were heavenly phenomena. They were not meteorological phenomena, which is quite important because people figured that the heavens were unchanging. So Tycho proved that certain things like that supernova and comets are heavenly phenomena, and yet they are changing. So as we mentioned, Tycho had kind of a hybrid system because he was not able to account for the ideas of either Ptolemy or Copernicus. So he went back to this hybrid system that might have at least been partially motivated by Capella, who I mentioned before, who Copernicus himself had referenced. Capella placed the superior planets as orbiting Earth, but Mercury and Venus as orbiting the Sun. So similar to the ideas of Heraclides. Now Tycho simply took it a step further and said that all the planets are orbiting the Sun, except the Sun is orbiting around Earth. So there's Earth at the center, everything else going around the Sun, and Sun going around Earth. This was Tycho's idea. Pretty similar to Copernicus's idea. It's just a reference frame is shifted. Now, Tycho was trying to come up with a really good way of revising his tables and maybe come up with something better. So he hired a number of mathematicians to help, in particular a person named Johannes Kepler. And Kepler actually inherited Tycho's data when Tycho died suddenly in 1600. The way that this happened was he was at a dinner with the king, and the king was giving a very long-winded speech, and Tycho had had a bit too much to drink, but he thought it would be rude to get up and leave the table during the king's speech, so he simply held it, and he kept holding it, and it was, I guess, a bit too long, and it said that he died of either a ruptured bladder or kidney failure from not relieving himself. So, lesson goes, don't be like Tycho, go when you need to go. But in any case, Kepler inherited Tycho's data. Now, Kepler, unlike Tycho, first of all, you can see some differences in the stash. So Tycho has a very pronounced and very well-groomed mustache, whereas Kepler is a bit more scraggly. It's a bit more scraggly, but he still took some lessons from his teacher on that. But Kepler was a geocentrist. Or sorry, he was a heliocentrist. Tycho was a geocentrist. Kepler was a heliocentrist. He believed that Earth actually was moving. The reason that Tycho didn't believe that is, again, he did not observe parallax. So, Kepler inherited Tycho's data, and in analyzing these data very precisely, Kepler could not believe that Tycho would make these types of observations in error. In other words, the sizes of the differences between the predictions of Tycho's data, or sorry, Tycho's model and Ptolemy's model and Copernicus's model were a bit larger than what was the precision of Tycho's observations, which were extremely precise and accurate. So Kepler realized that the whole idea must be wrong. So Kepler, being a good mathematician, tried a bunch of things. And as he did so, he discovered 3 laws of planetary motion. The first law is that each planet moves around the sun in the orbit of an ellipse, with the sun at one focus of the ellipse. What that means, we're going to get to that soon. Second law, if you were to draw a straight line between the sun and the planet, that line will sweep out equal areas during equal time intervals. Again, what that means, I'll show that soon. And the third law is that the squares of planets' period of revolution are in direct proportion to the cubes of the semi-major axes of the orbits. Now, for the first law, in order to draw an ellipse, one thing that you can do is you can take 2 tacks and tack them down in different locations and have a closed, loose piece of string that you end up making taut by drawing a pencil to the outside, and you just kind of draw around as long as that remains taut. So you can see what's going on here. The distance between the 2 tacks is constant, and the total distance when you go from one tack to the pencil plus the other tack to the pencil is also constant. So what is an ellipse? An ellipse is the set of all points that are equal to a fixed sum of distances from 2 different points. In other words, as you go around, the short distance will end up changing, the long distance will end up changing, but the sum of those will always be the same. That's what an ellipse is. Now, Kepler, being a mathematician, he knew of lots of different ovular geometric figures, lots of different types of ovals, and things like egg-shaped things, things that look like rectangles but are rounded at the edges. He tried all of those types of things for the motions of the planets, and he found that he got by far the best fit if he assumed that the orbits of the planets were elliptical, with the sun being at one focal point. Turns out there's nothing special about the other focal point. So the major axis is the widest diameter of the ellipse, the semi-major axis is half of that distance, and it just so happens that the average distance of a planet from the sun is also equal to the semi-major axis of the ellipse. Now there's something called eccentricity for an ellipse. The more non-circular it is, the larger the eccentricity, such that 0 is a perfect circle and 1 is a parabola. So the closer you are to 1, the more elongated the ellipse is. So comets have orbits that have eccentricities often relatively close to 1, whereas the planets generally have eccentricities pretty close to 0, with 2 exceptions. Mercury, but Mercury's orbit is small enough that it's hard to notice, and Mars. Mars has a quite noticeably elliptical orbit, and it was because of that nobody was able to get their data to fit Mars. You would have to draw infinitely many epicycles on top of epicycles, where all of your epicycles are circles, in order to approximate an ellipse. That's why it never worked with Mars. So again, here you can see some planetary orbits with some comet orbits laid on top. Some vocabulary terms. Perihelion is the closest distance of an orbiting object to the sun. Aphelion is the farthest distance. So kind of remember with this from Earth. In the case of Earth, closest distance in orbit around Earth is called perigee. Farthest distance is apogee. If you're going around the sun, it's perihelion and aphelion. If you're going around the center of the galaxy, it's paragalacticon and apogalacticon. If you don't know what you're going around, you just say periapsis and apoapsis. Going around Jupiter is perajove and apojove. Around Neptune is paraposeidion and apoposeidion. So they have cool names for a lot of these types of things. Some optional math that we're not going to get too much into, and you don't need to know for the test if you're in my class, is that if you know the eccentricity of the ellipse, then the perihelion is equal to the semi-major axis times 1 minus the eccentricity, where A is the symbol for semi-major axis. That is the distance between the center and one of the long ends. Aphelion is equal to A times 1 plus E. So generally speaking, the planets have eccentricities of less than 0.1. Mars is around 0.1. Mercury is 0.2. But Venus, I think, is like 0.00 something. And same might be true of like Jupiter and Neptune and stuff like that. So, quick optional example with this. How about Comet Halley? So Halley's comet has a semi-major axis of 17.8 astronomical units, just an observational fact, and an eccentricity of 0.967. What's its perihelion and aphelion? Well, here you have your givens. And now you have the formula. The perihelion is A times 1 minus E. Plug in your givens. Eccentricity does not have any units. It's, by definition, actually a ratio. So, no units. So 1 minus 0.967 is 0.033, and multiply that by 17.8 astronomical units. Halley's comet gets as close as less than 0.6 astronomical units from the Sun. In other words, when it's closest to the Sun, it's closer than Venus. In fact, that's why comets behave as they do. As they get close to the Sun, you end up having all of the ice and everything evaporate and sublimate, and ends up creating that nice, brilliant tail. What about its aphelion? Its aphelion is 35 astronomical units. 1 plus 0.967 times the 17.8 unit astronomical unit semi-major axis. So 35 astronomical units. That takes it out past Neptune when it's farthest from the Sun. And as we're going to soon see, it spends a lot of time there. So we already discussed these terms, peri and apo. Now, Kepler's second law. Kepler's second law says that a line connecting Sun and planet sweeps out equal areas during equal time intervals. So a result of this is that the planets move faster when they're closer to the Sun. Here's why. Here's a particularly elliptical orbit where near aphelion, the distance from the Sun is quite a bit farther than it is near perihelion. So because those distances are farther, in order for these sectors to have the same area, the object is moving more slowly when it's farther from the Sun than when it's close to the Sun. But the areas are the same, so it's moving a lot faster when it's closer to the Sun. Now, Kepler did not know the reason for this. Just being a good mathematician, he saw it as an observational fact. It wasn't until Isaac Newton that we figured out why that's the case. Isaac Newton was able to derive the shapes of the planetary orbits as ellipses, and in so doing, also demonstrated Kepler's second law. In fact, kind of going a bit further, we recognize that Kepler's second law is actually a result of the conservation of angular momentum of the orbiting bodies. So, in any case, though, it's going faster when it's closer to the Sun, slower when it's farther away, and it's doing so in such a way that these areas, the area of sector S43 is the same as the area of sector S12. Okay, so let's see how that actually looks by looking at the Stellarium program. Sorry, not the Stellarium program, but the My Solar System program from PhET. So here is the PhET website, phet.colorado.edu, and you can go to simulations. In fact, I have the entire URL up here in case you want to play around with it. It's a great website. So what I'm going to do is I'm going to change a few things from their default values. I'm going to make the mass of body 2 0 because I don't want it affecting the Sun. And also, I'm not going to have the Sun initially moving. But here we have the motion of this object. So you might be able to tell that it's going a little slower when it's farther from the Sun, faster now, slower here, and faster here. Now let me reset this. I'm going to actually start it way the heck out here. Let's start it at about 210. No, that's not far enough. How about 320? Okay, so 320, it's starting out here, yeah, but it's in the instructions. Let's bring it back out a little, so maybe 240. There we go. And I'm going to slow it down quite a bit for its initial velocity. I could just change that by this, and you see the numbers are changing. But I can also type in here and change the numbers. But let's see how this goes. Here you can tell it's going quite a bit faster when it's closer to the Sun, and quite a bit slower when it's farther away. Let's slow it down a little bit more. Oh, we can do better than that. I want a really strongly elliptical orbit so that you can really see what's going on here. Okay, that's good. So we'll make it even more like 36. So there we go. Going real slow out here. Then it really swings around the sun and then spends a lot of time out here. This is what comets do. In fact, most comet orbits are a lot more elliptical than this. Like they will come really, really close to the sun and then go way far out there. And that's because of the fact that the total energy of their orbit is very close to zero, just because of how they formed and got flung out during the solar system's formation. We'll have more to say about that in the solar system unit. But as you can see, they spend the vast majority of their time very far from the sun. So even though they have these nice, beautiful long tails when they get close to the sun, that's only a very small segment of their lifetimes. And again, a typical comet might have an orbit that has a period of, say, 100,000 years and spend only a few months in the sun's vicinity. Okay, so, but yeah, this is kind of Kepler's second law, a result of Kepler's second law, that it's going a lot slower when it's farther from the sun and a lot faster when it is closer to the sun. One more orbit, there we go. And let's bring us back to the discussion. So here's another nice depiction of this, which I took from the second edition of the Carolyn Osley book, Introduction to Modern Astrophysics, where each dot represents an equal time interval in this particular orbit. And so you have the dots really close together when it's far out. It spends the vast majority of its time out here, and pretty far apart when it's close to the sun. So it really swings around quickly when it's close to the sun. Kepler's third law says that the distance, in fact, more precisely, the semi-major axis cubed is equal to the period squared. Now, for whatever reason, a lot of times when people write Kepler's third law, they use the symbol capital P to indicate the period, whereas normally in physics and astronomy, the symbol for period is capital T. I'm going to use both just so that you kind of get used to seeing either one. But the whole point is the period squared is equal to semi-major axis cubed if you are using the right units. Now, what does that mean to be using the right units? So again, the semi-major axis is half the length of the long end of the ellipse, or the average distance of the planet from the sun. And just some quick examples. Let's consider Mars. Well, Mars has an orbital period of 1.88 years and a semi-major axis of 1.52 astronomical units. So 1.52 cubed turns out to be the same thing as 1.88 squared. So apparently the units that you want to be using when you're dealing with Kepler's third law, at least for objects going around the sun, are distance units of astronomical units and period units of years. So long story short, what that means is that for objects going around the sun, the orbital period in years squared is equal to the semi-major axis in astronomical units cubed. So let's try this with Jupiter. Jupiter has an orbital period of about 11.86 years. Well, 11.86 squared is 140.7, and that's equal to its semi-major axis cubed. So this is equal to a cubed, so we need to take the cube root to get the semi-major axis by itself. And when you do that, you get 5.2 astronomical units, which is indeed the semi-major axis of Jupiter. And what about Halley's Comet? 76 years to go around the sun. Well, here we go. 76 squared is equal to a cubed. So take the cube root of 76 squared. Let's see, 76 squared is going to be 5776. And when you take the cube root of that, you get 17.9 astronomical units. Now keep in mind, doing it that way only works for planets in our solar system orbiting around the sun. If it's not orbiting around the sun, if it's mainly orbiting around something else, like say a moon orbiting around Jupiter, or if it's a planet orbiting around some other star, you have to go back to the original form of Kepler's third law. The original form is that for any system, the period squared is proportional to the semi-major axis cubed. So what does proportional to mean? It means that it's equal to it times some number that we call the proportionality constant. So we'll just call that proportionality constant K. So what it means to be proportional to? Well, let's see what we can realize from this. Let's say that we say quantity A is proportional to quantity B. So A is proportional to B. What that means is that if you have two data points, say, for two different situations that all fall under the same roof, so to speak, call it point 1 and point 2. Well, for point 1, A1 is equal to B1 times that constant K. And A2 is equal to B2 times that constant K. So because of that, what you can do is you can take the ratio of A1 over A2, or A2 over A1, whichever you prefer, and realize that if A is proportional to B, that means the ratio of A's is equal to the ratio of B's. Why equal to? Because, after all, I mean, these are two true statements. You can always divide one equation by another equation. So divide the equation A1 equals KB1 by the equation A2 equals KB2. And you get A1 over A2 equals B1 over B2 because the K's cancel. Now, what if each quantity is raised to some power? Well, if it's raised to some power, A to one power is proportional B to the other power. You can do the same mathematical reasoning that we just showed and show that the ratio of A's to that power, which we're calling X, is equal to the ratio of B's to that power, which we call Y. This is incredibly useful, not just in Kepler's third law, but in a variety of physics situations. In Kepler's third law, since period squared is proportional to semi-major axis cubed, that means that if you find two different objects that are orbiting around the same body, then the ratio of their periods squared is equal to, not just proportional to, but equal to the ratio of their semi-major axes cubed. So here's an example of where this can be used. Let's say you've discovered a star around which you found a planet. You studied that planet for a while, and you found that that planet has a semi-major axis of 1.26 astronomical units from the star, and it takes it 226 days to go around the star once. And here we're saying the orbit is circular, so the semi-major axis is the same thing as the distance. But if it's not circular, you just take the semi-major axis. Well, let's say as you're going through your old telescope observations, you notice that there's another planet that's at 2.71 astronomical units from that star. Well, what's its orbital period? Do you need to watch it for a very long time? Well, by Kepler's third law, you don't need to watch it. All you need to do is set up that ratio. So we have our givens here. We're looking for the orbital period of the new planet. And since I called the new planet Planet 2, I decided to put that in the numerator so that I don't have to do too much in the way of cross-multiplying, just have to do cross-multiplying once. So in any case, the ratio of periods squared is equal to the ratio of semi-major axes cubed. So we plug in our givens, and in fact, we could have just multiplied both sides by t1 squared at the very beginning, and then taken the square root, and then plugged in our givens, and we wouldn't have as much to do on the calculator. So taking the square root of this, you just get 226 days times this ratio to the 3/2 power, if you were to do it that way. But just doing it the way that's on the slide, you can plug this into your calculator and find that the orbital period squared of the new planet is 508,175 days squared. That's days squared for period squared. Well, we don't want period squared, we want period. So you need to take the square root of both sides of this thing to get period by itself, which involves taking the square root of 508,175 days squared. So you get units of days, and the square root of 508,175 is about 713. So now that you have found this other planet, 2.71 astronomical units from the star, a quick calculation tells you that the orbital period is 713 days. If it turns out that it wasn't 713 days, that would tell you that the orbit is elliptical. So that's how Kepler's third law can be used to deal with a variety of these types of situations. Again, why is the law true? Kepler didn't know. Kepler didn't know. It was left to Isaac Newton to figure out why the law is true. But it's incredibly useful. It is still used in modern astronomy today. So now we move on to Galileo, Galileo, Galileo Galilei. So, was he just a poor boy and nobody loved him? No. He's famous for a variety of reasons. He was a gifted physicist, and he also made a number of telescope observations. Now, Galileo did not invent the telescope. It was invented at least as early as 1608 by this guy, Hans Lippershey. It's spelled both Lippershey. I've forgotten the whole story on that. But Galileo was, as far as we can prove, the first person to use a telescope to study the sky and record and explain what he saw. Now, among a number of things that he reported, he found that our moon is not a perfect world. It has mountains and valleys and craters. He found that the Milky Way is made up of countless individual stars, this band of light across the sky that just looks like this Milky Way. In fact, Milky Way galaxy is a redundancy because galaxy comes from the word galactose, having to do with the sugar and milk. But the Milky Way is made of countless individual stars that to our eyes just look blended together to make this nice band of light across a dark sky that you can't see from Northern Virginia. He found that Jupiter is surrounded by 4 moons. Now, one of the arguments that people had been making against the heliocentric model was that if Earth was going around the sun, we would leave the moon behind. Again, they didn't understand universal gravitation at that time, or inertia. So it was like, yeah, if Earth's going around the sun, it would leave the moon behind. Well, no matter who you ask, whether you ask Ptolemy, whether you ask Kepler, whether you ask Copernicus, everybody agreed that Jupiter is going around the sun, but it's not leaving its moons behind. Galileo watched the moons carry many orbits around Jupiter as Jupiter was going around the sun. So this showed that bodies other than Earth could be the center of motion. So here's a view of Jupiter with its moons through a small telescope. You can see Jupiter's moons with binoculars. If you know what to look for, it's just they're going to be little points of light pretty much in a line around where Jupiter is. You also could see them with your unaided eye if it wasn't for the fact that Jupiter was so bright and blots out their brightness because of being relatively close. So you need binoculars in order to resolve the moons from Jupiter, as opposed to be able to see their light. As a side note, Galileo also, believe it or not, discovered the planet Neptune. He's not given credit for that because he did not recognize it for what it was. He thought it was a star, but he very definitely observed Neptune. Now, he discovered sunspots, or at least he rediscovered sunspots. Remember, the ancient Chinese observers had been studying sunspots for a while. And very importantly, he discovered the phases of Venus. Now, the fact that Venus has phases is actually not surprising, as we will discuss soon. Now, in the year 1632, Galileo published his dialogue concerning the 2 chief world systems, which advocated the Copernican model. Now, this book was banned by the Inquisition, and Galileo was forced to recant, and he was placed under house arrest until his death. There's actually a long story surrounding this, which I do want to explain. So, here's the story. Galileo discovered that Jupiter has moons, and that the moons are going around Jupiter. But that by itself did not prove that Earth was going around the sun. After all, everybody agreed that Jupiter was going around the sun, or at least going around something. Everybody agreed that Jupiter was moving. They either thought it was going around Earth, or they thought it was going around the sun. But Galileo discovered phases on the planet Venus, and he discovered phases that shouldn't exist in the Ptolemaic system. How did Ptolemy explain the fact that Venus never goes far from the sun? So here was Ptolemy's idea. Ptolemy believed that Venus was on an epicycle that was always constantly on a line between Earth and the sun. such that Venus was always going on this epicycle. Never mind the fact that Venus should appear much brighter than it does at certain points in its orbit, if this was the case, but this was at least how Ptolemy and his followers explained it. But if this is the case, Venus should only ever exhibit one phase. It should only ever exhibit a crescent phase. The fact that Galileo saw not just crescent phases, but quarter phases and even gibbous phases, when Venus was kind of on the far side of the sun, proved that Venus goes around the sun. Galileo proved that Venus orbits the sun. Did people accept this? Generally speaking, yes, they accepted this. Great! You've proven that Venus goes around the sun. Congratulations! You are a gifted astronomer. You still haven't proven that Earth goes around the sun. So Galileo had to come up with some arguments for this. Now, in his argument about Earth going around the sun, he believed that Earth was going around the sun and that this could be proven by the sloshing motion that a rotating body would have as it is also orbiting around something else. Interestingly enough, this actually contradicts Galileo's own ideas with physics and mechanics and the law of inertia. Like he first noted that things fall at the same rate regardless of their composition, and he understood the law of inertia, basically Newton's first law, that objects tend to maintain constant velocity, which kind of leads to this idea that you can only talk about relative motion. But yeah, objects maintain constant velocity unless there's a net force acting on them. So Galileo understood that, and his explanation of the idea that there would be a sloshing motion on Earth, which would cause 2 high tides per day as Earth orbits around the sun while rotating, this was completely contrary to his own physics. Now, he was proposing that Earth went around the sun long before he got in trouble for it. He was teaching this back in the 16 teens, and there were some Dominican friars who were having some trouble with this. They didn't like him teaching this. Galileo was a high-level person in the church, so he didn't answer to all that many people. I mean, of course, he answered to the Pope, and he answered to some cardinals, but not all that many other people. He was in a fairly high position. So he was teaching this as just part of his teachings, and some of these friars were upset about it. So they complained to the Pope, and they also complained to a cardinal to whom Galileo answered, but that cardinal was actually one of Galileo's really good friends, so those complaints did not get very far. And when the friars brought their complaints all the way to the Pope came back to Galileo and said, I've heard these complaints and I understand these complaints, but I will tell you that they will not get anywhere, quote, as long as I shall live. Unfortunately, that didn't turn out to be long enough. A few years later, that Pope died. The person who took that Pope's place, though, was none other than Galileo's good friend, the Cardinal. And so it seemed like everything was going to be going really smoothly. But here's the thing. What was going on in the 1600s? I mean, Copernicus had taught this back in the 1500s. Nobody complained about it then. Well, here's the thing. In the 1600s was the Counter-Reformation. Remember, Martin Luther nailed his 95 Theses to the church door back in the 15 teens, and that was kind of the initiation, or at least that's often credited as being the initiation of the Reformation. Well, then there came this Counter-Reformation from the Catholic Church to show that they were kind of keeping in line with everything, and they needed to at least show the appearance of taking a strong stand on certain issues, including issues of, at that time, what were seen as biblical inerrancy. In the book of Joshua, there is this idea there's a story where there's a battle that's about to be held, and the idea is that the battle will be won if it is completed by the end of the day. So Joshua ends up praying to God to, quote, stop the motion of the sun through the heavens, and allow the battle to finish before the end of the day. And that was seen by many people. Again, if you're going to, some people would say, if you're going to interpret the Bible literally, you have to interpret it literally in all contexts. That was seen by some, that literal interpretation was seen as proof that it's the sun that goes around Earth as opposed to the other way around. And, I mean, people often just didn't think of things back then the same way as we think of things right now. In terms like, okay, fine, you can maybe believe that it's the literal word of God, but maybe you don't necessarily believe that the way that we understand things is the way that God always sees things. But in any case, Galileo was preaching that Earth was going around the sun, and this bothered some people, but it did not bother the Pope, and it did not bother his friend the Cardinal. But then around 1630, the Cardinal started getting more and more, the new Pope started getting more and more complaints, though I guess he wasn't the new Pope anymore in 1630, and he went to Galileo and said that he needed to kind of temper down his teachings on this because it was causing a lot of consternation in the church. So Galileo asked if he could have permission to publish his theories in this dialogue concerning the two chief world systems. Now, his main theory about how Earth was moving around the sun had to do with this sloshing motion of Earth as it's rotating and going around the sun. Well, he believed that that's what caused the 2 high tides per day. Whereas the people in the church were often coming back and saying, no, that's not what's causing the 2 high tides per day. The moon is causing the 2 high tides per day. They didn't understand exactly the force of gravity with the moon, but they did understand that there was a direct association between the moon and the 2 high tides. They were always trailing by the same amount in terms of moon's orbit around Earth. So they did actually have that part right. Galileo was wrong about his theory in this case, and in this case the church was right. But he asked the Pope for permission to publish this basically proof of Earth going around the sun. And the Pope granted him permission. He said, you may do this as long as you make it clear in the end, as long as you offer a disclaimer that it's possible for God to act in ways that make things appear to be the case, but that are actually otherwise. As long as you have that disclaimer in there, it's okay for you to publish this. So Galileo wrote this book as really a, dialogue concerning the 2 chief world systems. He wrote it kind of as in the form of a debate between 2 people, the one who believed that Earth was going around the sun, as demonstrated by the sloshing motion causing 2 high tides per day, and the other was Simplicio, the simpleton, who believed that the sun was going around Earth and the tides were caused by the moon. And then there was a third party in there who was kind of moderating the debate, so to speak. So they didn't have microphones or anything like that, so that there weren't any you didn't have to mute anybody's mic or anything like that while one was interrupting the other. But in any case, in this dialogue, the way that Galileo wrote it, Simplicio was eventually proven wrong, and finally, at the end, Simplicio said, I will accept what you have demonstrated, but it could be that God is acting in a way to make us see things in a way that is different from the reality. There it is, the Pope's words in Simplicio's, out of Simplicio's mouth. Let's just say that the Pope, who had been sticking up for Galileo for a very long time and time again, fighting against all of his detractors, felt like he was stabbed in the back. This was the event that caused the Pope to summon Galileo before the Inquisition and force him to recant his errors and got him placed under house arrest. It was this backstabbing of his previous best friend who had been defending him all this time. So let's just say that there's a lot more to this than just an idea of belief systems. There were a lot of politics in this whole thing that eventually got Galileo banished in house arrest. But he was still productive during his house arrest. This was during the time when he published a lot of his ideas in physics that we have already brought forth. So you might wonder, though, why was Galileo persecuted and not Kepler? So, as I already mentioned, there was the fact that Galileo kind of backstabbed the Pope and made fun of him in this allegory. But another thing was that Kepler tended to write more in the common language as opposed to the language of the Church. And in addition to, well, not backstabbing the Pope. So, Kepler was also more just about direct observational science. So, Galileo did not succeed in proving that Earth went around the Sun. He did not succeed in this. Instead, or at least he did not succeed in convincing people of the time that Earth went around the Sun. Kepler succeeded in convincing most of his associates at the time that Earth went around the Sun, because it was actually Kepler's third law, which came a bit after his first two laws, that ended up having this effect. The fact that his third law was able to make specific, verifiable predictions that could have easily turned out to have been wrong and completely disproven his whole model. The fact that this ended up working in the case of Kepler was what got people onto the side of the heliocentric system. So that is the story of Copernicus, Tycho, Kepler, and Galileo, and we're going to save our discussion for Isaac Newton until next time. So until then, I'll invite you to add questions and comments into the comment section on YouTube, and thank you for watching.